Today we are going to discuss one of the most important paradoxes in microfluidics and lab-on-a-chip research, the PDMS paradox. This is a critical issue that affects the validity of countless organ-on-chip experiments. PDMS stands for polydimethylsiloxane. It is a silicone-based polymer that has become the gold standard material for microfluidic device fabrication. At the molecular level, PDMS consists of repeating units of silicon atoms bonded to oxygen atoms, with methyl groups attached to the silicon. This gives it unique properties. Let me ask you a question. Why has PDMS become so dominant in microfluidics research? The answer lies in its remarkable combination of properties. First, PDMS is optically transparent, which means you can easily image cells and biological processes using standard microscopy. Second, it is gas permeable. This is crucial because cells need oxygen to survive, and PDMS allows oxygen to diffuse through the material. Third, it is biocompatible. Cells can attach to it, grow on it, and survive for extended periods. Fourth, and perhaps most importantly, it is incredibly easy to fabricate using soft lithography. You can make complex microfluidic devices in a matter of hours. And fifth, it is very inexpensive. A bottle of PDMS precursor costs a few $100s and can make hundreds of devices. Here is a typical PDMS microfluidic device. The channels are molded into the PDMS, and cells can be cultured inside these channels. The material is flexible, transparent, and perfect for prototyping. But here comes the paradox. The same properties that make PDMS wonderful for rapid prototyping also make it terrible for quantitative studies involving small molecules. PDMS is highly hydrophobic. Remember those methyl groups? They make the surface water repelling. Let me ask you, what does this hydrophobicity mean for drug molecules? Many drugs are also hydrophobic, and hydrophobic molecules love to interact with hydrophobic materials. Here is what happens. You have a drug solution flowing through the channel. The drug molecules start to partition into the PDMS bulk material. They are absorbed and adsorbed by the polymer network. There are two distinct mechanisms by which molecules disappear from your solution. Absorption is when molecules actually dissolve into the bulk of the PDMS material. They diffuse throughout the entire polymer volume. Adsorption is when molecules stick to the PDMS surface. They bind to the channel walls. Both processes deplete the drug concentration in your solution. This is catastrophic for dose-response experiments. Let us quantify this problem. The key parameter is the partition coefficient, which we call K. K equals the concentration in PDMS divided by the concentration in solution at equilibrium. For hydrophobic drugs, K can range from 10 to 1000 or even higher. This means the drug concentration in PDMS can be 1,000 times higher than in your solution. For K equals 100 in a volume ratio of 10. Solving for the final concentration in solution, we get C initial times channel volume divided by channel volume plus K times PDMS volume. The final concentration becomes C initial divided by 1001, which is approximately C initial divided by 1000. You lose 99.9% of your drug to the PDMS. Your actual concentration is 1,000 times lower than you think. Here is a visual representation. You think you are dosing your cells with 1 micromolar of drug. But in reality, the cells are seeing only 1 nanomolar. This is a 3 orders of magnitude error. The situation is even more complex because absorption is time-dependent. It does not happen instantaneously. The rate of concentration change is proportional to the concentration, with a rate constant K absorption. In the initial phase, there is rapid surface adsorption. This happens in seconds to minutes. In the later phase, there is slow bulk absorption as molecules diffuse into the PDMS. This can take hours to days. This graph shows the concentration decay over time. The drug concentration drops rapidly at first due to surface effects, then continues to decline slowly as bulk absorption occurs. What are the real consequences of this in actual experiments? First, dose-response curves are completely wrong. Your EC50 values are meaningless because you do not know the actual drug concentration. Second, Drug efficacy appears artificially reduced. A drug that should work at 1 micromolar appears ineffective because the actual concentration is 1,000 times lower. Third, time course experiments are unreliable because the drug concentration is changing throughout your experiment as absorption continues. Fourth, comparing results between devices of different geometries gives inconsistent results because the volume ratios are different. Here we see two devices with the same nominal drug input, but device A has more PDMS volume relative to channel volume, so it absorbs more drug. The cells in device B see much higher concentrations. Your results depend on device geometry, not biology. Now let us ask, which molecules are most affected by this problem? Hydrophobic small molecules show very high absorption. This includes many drugs like steroids, immunosuppressants, and anti-cancer agents. Specific examples include dexamethasone, cyclosporin, and paclitaxel. These are commonly used in organ-on-chip studies and are severely affected. Large proteins are less affected by bulk absorption because they cannot easily diffuse into PDMS. However, they can still adsorb to surfaces. Very hydrophilic molecules like glucose or salts show minimal absorption. They stay in the aqueous phase. This diagram shows the relationship between molecular size and hydrophobicity versus absorption. Small hydrophobic molecules like steroids have partition coefficients over 1000. Peptides are intermediate. Large proteins have partition coefficients less than 1. Let me show you some actual measured partition coefficients from the literature. Dexamethasone has a partition coefficient of approximately 3000. Cyclosporin A is even worse at about 5000. Even fluorescent dyes like rhodamine are affected, with K around 400. Estradiol, an important hormone, has K around 1500. These are not small effects. These are massive systematic errors that invalidate quantitative conclusions. So what can we do about this problem? There are several strategies researchers have developed. Strategy 1 is surface modification. You can coat the PDMS channels with materials that reduce absorption. Parylene coating involves vapor depositing a thin polymer layer that is less absorptive than PDMS. PEG coating, polyethylene glycol, reduces protein adsorption and can help with small molecules too. The problem is that coatings can delaminate or degrade over time, especially with flow and cell culture. Strategy 2 is to use alternative materials instead of PDMS. Thermoplastics like cyclic olefin copolymer, polymethyl methacrylate, or polycarbonate have much lower absorption. Glass has essentially zero absorption and is chemically inert, but it is expensive and difficult to fabricate. Hydrogels can be used for certain applications where their properties are beneficial. The trade-off is that you lose the ease of fabrication that makes PDMS so attractive. Here is the trade-off. PDMS is easy and cheap but has high absorption. Thermoplastics are harder to work with and more expensive but have low absorption. You have to choose based on your experimental needs. Strategy 3 is to pre-saturate the PDMS with your drug before starting the experiment. You pre-incubate the device with a high concentration of your drug for hours to days. This allows the PDMS to reach equilibrium and absorb as much drug as it can. Then you start your experiment with the same drug concentration, and there should be no net absorption. The problem is this wastes a lot of expensive drug, and it takes a very long time. Strategy 4 is to use carrier proteins like albumin in your medium. Bovine serum albumin binds hydrophobic drugs and can reduce their effective partition coefficient. The effective partition coefficient is reduced by a factor of 1 plus the binding constant times the BSA concentration. The problem is this also changes drug bioavailability to cells because the protein-bound drug may not be active. Strategy 5 is to mathematically correct for absorption after measuring it. You measure the actual drug concentration in the device using analytical methods. This can be done with mass spectrometry or by using fluorescent drug analogs. Then you apply a correction factor to convert nominal concentration to actual concentration. The problem is this requires significant extra work and specialized equipment. Let me walk through a practical example of how this affects a drug screening assay. Imagine you are testing an anti-cancer drug in a lung on a chip device made of PDMS. The drug is paclitaxel. The known IC50 in standard culture plates is 10 nanomolar. You prepare a 100 nanomolar solution for your chip experiment, expecting a strong response. But paclitaxel has a partition coefficient of approximately 2000. Your device has a channel 100 micrometers wide and 50 micrometers tall. The volume ratio is approximately 20. The actual concentration is 100 nanomolar divided by 1 plus 2000 times 20, which equals 0.0025 nanomolar. The actual concentration is 4,000 times lower than you think. You are dosing at 0.0025 nanomolar when you think it is 100 nanomolar. The result is you see no cytotoxic effect and incorrectly conclude that the drug does not work in your organ-on-chip model. This graph shows the expected dose-response curve in green versus the observed curve in red. The expected curve shows strong response at 100 nanomolar. The observed curve is flat because the actual concentration is far below the IC50. Organ-on-chip devices face additional challenges beyond simple microfluidics. Challenge 1 is that organ-on-chip studies often run for days to weeks. This allows complete equilibration and maximum absorption. Challenge 2 is that cells in 3D microenvironments may metabolize drugs differently than in plates, making it even harder to determine true concentrations. Challenge 3 is that many organ-on-chip studies use multiple drugs or hormones simultaneously. Each compound has a different partition coefficient, leading to complex interactions. Challenge 4 is that it is very difficult to validate results against known pharmacology when the actual drug exposure is unknown. Let me ask another question. Can we predict absorption theoretically from molecular structure? The answer is partially. We can use the octanol water partition coefficient, called log P. Log P is the logarithm of the ratio of concentration in octanol to concentration in water. Log P correlates reasonably well with PDMS absorption because PDMS is also hydrophobic like octanol. An approximate empirical relationship is Kpdms equals 10 to the power of 0.8 times log P plus 1.5. For example, if log P is 3, K is approximately 1000. If log P is 5, K jumps to approximately 30,000. This plot shows the relationship between log P and log K. There is a clear positive correlation. More hydrophobic molecules have higher partition coefficients. Let me give you some concrete recommendations if you are working with organ-on-chip devices. Recommendation 1. Know the log P of all your compounds. Look them up in databases or calculate them. Recommendation 2. If log P is greater than 2, be very cautious. Expect significant absorption. Recommendation 3. Measure actual concentrations if possible using analytical chemistry methods. Recommendation 4. Consider alternative materials for quantitative dose-response studies, even if prototyping is harder. Recommendation 5. Always report device geometry and volume ratios in publications so others can assess absorption effects. Recommendation 6. Pre-saturate devices when using hydrophobic drugs, despite the cost and time. Recommendation 7. Use carrier proteins judiciously and report their concentrations. Now let me discuss some recent advances in addressing this problem. Researchers are developing new materials like fluoropolymers that combine PDMS-like processability with lower absorption. Hybrid devices use PDMS for the bulk structure but incorporate glass or thermoplastic channels where drugs flow. Real-time concentration monitoring using integrated sensors is becoming more feasible. Computational models are being developed to predict absorption based on device geometry and compound properties. Here we see two approaches. On the left is a hybrid device with PDMS structure but a glass channel insert. On the right is a pure thermoplastic device. Both reduce absorption but require more complex fabrication. Let me step back and discuss the bigger picture. What does this mean for the validity of organ-on-chip data? Many published organ-on-chip studies may have incorrect drug concentrations by orders of magnitude. Comparisons to in vivo pharmacology data can be highly misleading if absorption is not accounted for. Regulatory agencies like the FDA are increasingly concerned about this issue as they evaluate organ-on-chip platforms for drug testing. There is an urgent need for standardization and best practices in the field. This is not just a PDMS problem. Other materials can have their own issues like leaching plasticizers or having poor optical properties. Let me share a historical example that illustrates how serious this problem can be. A research group compared the same drug response assay in PDMS devices versus glass devices. In PDMS devices, the EC50 appeared to be 10 micromolar. In glass devices with identical cell culture, the EC50 was 10 nanomolar. 3 orders of magnitude difference caused purely by the device material. The PDMS result was completely wrong and would have led to incorrect conclusions about drug potency. This comparison shows the dramatic difference. Same cells, same drug, same assay protocol. Only the device material changed, yet the measured EC50 differed by 1,000-fold. Let us quantify the uncertainty introduced by PDMS absorption. For a typical drug screening assay in a PDMS device, geometric variations between devices introduce uncertainty of a factor of 2 to 5. Different batches of PDMS can vary by a factor of 1.5. But absorption uncertainty is a factor of 10 to 1,000, completely dominating all other sources. A rough estimate of total concentration uncertainty is K times the volume ratio times a factor of about 0.5. This makes rigorous quantitative pharmacology nearly impossible in standard PDMS devices. So what is the path forward for the field? We must accept that PDMS is great for rapid prototyping and proof of concept studies, but not for quantitative drug testing. We need to transition to better materials for serious drug efficacy studies, even if fabrication is harder. We should develop and openly share correction methods and analytical protocols. The community should publish negative results and direct material comparisons to build knowledge. We must educate new researchers entering the field about this critical issue from day one. The conclusion is to use the right tool for the right job. PDMS for biology and proof of concept. Other materials for drug testing and quantitative pharmacology. Each has its place. Let me summarize the key points of this lecture. PDMS is genuinely excellent for rapid prototyping and biological studies where small molecules are not critical. But PDMS absorbs hydrophobic molecules massively, with partition coefficients from 10 to 10,000. This makes actual drug concentrations wrong by factors of 10 to 1,000. Many published organ-on-chip drug studies are likely affected by this issue. Solutions exist including coatings, alternative materials, and pre-saturation, but all require extra effort and have trade-offs. The field must address this issue systematically for organ-on-chip technology to gain credibility for drug development. Let me leave you with some final thoughts. This problem is a perfect example of how material science critically impacts biological experiments. No technology is perfect for all applications. Understanding limitations is as important as understanding capabilities. Good science requires acknowledging limitations and working systematically to address them. The PDMS paradox teaches us humility. A material that seems perfect can have hidden flaws that invalidate results.